you very much, Venkat. It's a pleasure to be talking to you today. We've been dazzled now by two talks talking about current technology and the future. And so now we're going to take a little trip down memory lane to look at the history of in-memory computing, which dates back to parallel supercomputing and continues now, as we see, it will continue well into the future. So as you heard, I'm Bill Bain. I've really devoted my career to parallel computing, having worked at Bell Labs, Intel, and more recently Microsoft. Our company, ScaleOut Software, develops in-memory data grid software for both storing fast-changing data and for operational intelligence. So I think I'd like to start by just talking about what are the generally accepted characteristics of an in-memory computing system. In-memory computing comprises both hardware and software, and it typically hosts data sets in primary memory and distributes computing across a cluster of servers employing data parallel computations, just so we can have a common definition. With that definition, we can reach deeply into the past and see where this all originated. Why use in-memory computing? The reason is because it allows you to process live, fast-changing data quickly and with scalable performance. And also you can analyze large data sets for big data. One of the things that we learned a while back is that scaling out is more cost-effective and scalable than scaling up. And that's one of the reasons we call our company ScaleOut Software. So in-memory computing actually dates back to the 1980s. I'm not sure if everybody knows this or nobody knows this, but the Caltech Cosmic Cube in 1983 could be considered one of the earliest, if not the earliest, in-memory computing system. It was created by Professors Jeffrey Fox and Chuck Seitz at Caltech. Jeffrey Fox was a physics professor, and he was trying to solve problems in high-energy physics and astrophysics. Chuck Seitz was working on microelectronics and chip simulation, and also needed a computing architecture to do it. So they created the first Caltech Cosmic Cube with 64 nodes using what we look at today, especially after hearing the last talk. This looks extremely ancient, and nevertheless, it shows us the foundations of in-memory computing, working with Intel 8086 and 8087 processors with a relatively small amount of memory, generating about 3.2 million floating point operations per second. Their goal was to have 1/10 the power of the Cray 1, but 100 times less the cost. And the original system cost about $80,000. So Justin Ratner at Intel recognized the future potential of the Cosmic Cube, and he started a group at Intel called Intel Scientific Computers, and he commercialized this technology with the first parallel supercomputer called the Intel IPSC-1 in 1985. Used the Intel 8286 processor because the 386 was not yet available. It had 128 nodes, 32 per box, as you can see on the right, and about 512 megabytes of memory for a full 128 node system, and used what's called a hypercube interconnect, which we'll look at in a minute. And that the goal of that was to shorten the time between communication between the nodes. So InCube was formed by some people that spun out of Intel also to build parallel supercomputers. They had 1,024 nodes and yet a smaller amount of memory, but also used the hypercube interconnect. IBM got into the business a little bit later, and then Intel also finally delivered a computer with 4,000 nodes in the Intel i860 chip, which you probably haven't heard of, but it was a numeric processing chip that was extremely fast for its time. And this system hosted 128 gigabytes of memory and used what's called a two-dimensional mesh architecture. And this also further drove down the communication delays between nodes of the system. So this commercialization of parallel supercomputers gave rise to the creation of numerous new applications. And you can see some of the fields in which parallel supercomputing was used. Computational fluid dynamics, for example, the design of the F-18 used parallel supercomputing in computational fluid dynamics for the leading edges of those wings, which are very complex. Structural mechanics like Nastran, weather simulations, climate modeling at NCAR, financial modeling on Wall Street, and distributed simulations for the military and also for logistics. So the challenge that these computers had and still have today is to extract scalable performance. How do you extract parallel speed up on a system with many processing nodes? And applications have a combination of code which can be fully parallelized and code which is sequential. And the sequential code and its overhead for communication can limit the overall performance. This was first observed by Gene Amdahl, who was the architect for the IBM System 360. And in 1967, he created what's called Amdahl's law for speed up of a parallel system with some number of servers. As you add servers, the parallel fraction of the code can get swamped by these delays from sequential code and communication overhead. So this Amdahl's law shows you that, for example, if you have 90% parallel code, the speed up still can't ever exceed 10x. The story that I heard was he was building vector processing units for a system like the IBM 360, and he found that no matter how fast the vector processing went, the overall system speed was still limited. You can look at this chart on the right and see that even at the top chart at 95% parallel code, the total amount of speed up eventually becomes limited. So this is a problem. How do you build a highly scalable compute cluster and still achieve scalable speed up? So one of the things people did, as we saw, is to build fast interconnects. And the original attempt with the Cosmic Cube and later with the IPSC1 was to use the Hypercube interconnect. And the reason for this is there was store and forward routing between the nodes. And with a Hypercube interconnect, you have logarithmic time between any two nodes. And that way you can reduce the total latency of communication. But still, with store and forward routing, it's substantial. Well, Bill Daly, who is a student of Chuck Seitz at Caltech at the time, in his PhD thesis, proposed a two-dimensional mesh with cut-through, or what he called wormhole routing, between the mesh routing chips at each node of the system. This dramatically reduced latency and really was a breakthrough for parallel supercomputing. Bill Daly went on to be a professor at MIT and then to be the chief scientist at NVIDIA, and is one of the luminaries in this field. So these networks have really helped to improve the problems of communication latency, but they are expensive and they're hard to build. So the problem is, how do you get scalable throughput for a system with many nodes in a cluster? And this was first tackled by Cleve Moeller, who was the creator of MATLAB. He worked at Intel Scientific Computers back in 1985 for a few years. And he also was one of the creators of LINPACK, Linear Equations Package, which is very popular at the time. And he was trying to make it run in a scalable way on the Intel Hypercube. And what he found is the LU decomposition algorithm would not scale. So you can see here that he was suffering from Amdahl's law throughput scaling when he had his first problem that he put on the Hypercube running on 128 nodes. No matter what he did, it wouldn't go faster. And that's because largely of the communication overhead. And what he realized is that by adding more elements to the matrix to make the matrix larger, so the problem size grew with the number of nodes in the system, he could approach linearly scalable throughput. And that's the basis of this notion of scalable throughput, namely that in order to extract the full performance out of a clustered system, an in-memory computing system, you need to scale the problem size to fit the number of nodes in the cluster. He also is known for coining the term embarrassingly parallel to describe scalable algorithms that have very low communication overhead, such as Monte Carlo simulations. And although it's not generally known that he was the one who coined that term, that's where it started. So this concept of scalable throughput was codified by John Gustafson at Los Alamos in 1988 with his Gustafson's law. And you can see in the chart below how when you scale the throughput, when you scale the workload to fit the number of processors or nodes in a system, then you can also scale the overall throughput. The purple line at the top shows Gustafson throughput for a fraction of parallel code, which is 90%. And you can see that the red line towards the bottom here, you can see the Amdahl's law restriction in scaling when you keep the problem size fixed. So you can see very clearly how scaling the problem size enables you to extract the scalable power of a parallel computing system hosting an in-memory computing problem. So let's look at how the architectures have evolved since the early 80s, starting out with these proprietary architectures using proprietary servers, if you will, called computing nodes, although they typically used obviously commodity processors, but not all did. N-Cube had its own processing node processor on the node. And so the interconnects were also proprietary. And typically these systems use their own operating system called a message passing operating system. Some were developed by the vendors like Intel and others by the national labs. And a standard version of message passing was developed by the labs and used by most people who ran on parallel supercomputers. Well, in the late 90s and early 2000s, clustering came into being, and because of its cost effectiveness. By running on commodity servers with now faster industry standard interconnects, people were able to avoid the cost of a parallel supercomputer for many problems they wanted to solve. And so then they had the opportunity to run with Linux or Windows in some cases, and also the emergence of middleware such as an in-memory data grid came into being with clustering. We'll talk more about that in a second. Then, of course, we've seen the evolution to virtual servers, and then more recently to cloud computing. So that's the natural evolution of the architecture of in-memory computing systems over the years since the earliest parallel supercomputers. Well, so what the problem we had with message passing is it's complex and error-prone and very difficult to implement, and also is typically used by scientists and not developers, software developers, so the codes were very complex. So to simplify the developer's task, in-memory data grids were created as software abstractions over the hardware. And I think this community knows about in-memory data grids very well, but looking back, the first commercial product that I could find, and feel free to send me a note to correct me, was TangoSol from coherence from TangoSol, pioneered by Cameron Purdy in about 2001. And then the other vendors that we know about have put their products on the market and evolved them since that time. The value you get from an in-memory data grid is that you're hiding the complexity of the in-memory computing hardware by giving the developer, the application developer, a global view of data stored across the memory of the servers, and an object-oriented view typically is what's used for in-memory data grids. And also this middleware software has mechanisms, as we know, for scaling transparently by adding servers and for handling the failure of a server or a network component with to give the overall system high availability to work with mission critical workloads. So this is the value that we get from in-memory data grids, but we see that they also can be used to host these data parallel computing algorithms that we saw earlier for the parallel supercomputers. So one of the things that we did at ScaleOut is to create a set of APIs which matched the ones used in the message passing operating systems of parallel supercomputers, namely a simplification of the MapReduce algorithm we call parallel method invocation. And with PMI, you run a user-defined method on all the objects in a namespace that is spread across the servers within a cluster, and then a binary merge is performed using an application-specific binary merge method to combine the results and return them in logarithmic time back to the client application. So this again is mimicking the behavior of a message passing operating system, but doing so with an object-oriented, location-independent view, and allows the developer to operate on objects instead of on raw data just stored in memory. And if constructed carefully, it can provide scalable speed up by reducing network use between the nodes. So what's important is to compute where the data lives. When running with an in-memory data grid, let the grid do the data parallel computation, and don't use a grid as just a cache in which the computation is performed externally to the grid itself. And we see this in a lot of our customer applications where they use the grid to host data, but then they extract it for computation on systems outside the grid. And that can lead to reduction in the scalable throughput we were just looking at. You can see an example of a financial services computation on the right, and you can see how the scalable throughput is compromised when the data is extracted from the grid instead of letting the parallel computation be run in the grid. So there are specialized software platforms for in-memory computing that focus on big data. And I think the one we all know about is Spark. Spark dates back to 2009. Matthijs Zacharia at UCB first created it. And of course, as we know, it's been commercialized. And he has gone on to be CTO of Databricks. So what it offers are specialized data parallel operators like map and reduce and filter in Scala and Java, and uses specialized form of data storage in memory called RDDs, resilient distributed data sets, because of its design for data parallel operations and big data. When you compare that to an in-memory data grid, an in-memory data grid generally serves the function of managing live data and not big data. So it's really designed to store individual objects with a key value store and to provide operational intelligence through data parallel computing. So let's look at the evolution of in-memory data grids to do streaming analytics. One of the challenges for streaming analytics is how do you achieve scalable speedup? So you can see that scalable speedup has been a theme of this talk, and it's a concept that was first encountered back in the 80s, and we still face it today, and we will face it in the future because it's fundamental to scalable in-memory computing. So with stream processing, the typical approach for APIs such as API Storm, Apache Storm, Flink, or Beam is to use a pipelined or distributed or a directed graph in order to construct a streaming application. And the challenge for that is that it's hard to extract full throughput because of the bottlenecks that can be created between pipeline stages and the need to map that algorithm to a set of servers. And also, if contextual data is used to introspect on the incoming data stream, then accessing that data from an offline store, such as a distributed cache or a database, encounters network bottlenecks. And all of these factors make it difficult to extract full scalable speedup in a streaming application. Now, there are certainly products that do it and do it very well, but we have to always remember the challenges of obtaining scalable speedup. So one of the techniques that we have employed at ScaleOut to address this issue is to use the digital twin model that came from product lifecycle management. Michael Greaves did this back at the University of Michigan, and we've applied it to the use in streaming analytics so that you can track individual data sources with contextual information. It also turns out that it maps very, very cleanly to an in-memory data grid. In fact, we discovered the use of this model by actually implementing the applications and realizing that we were building digital twins of data sources, and so we formalized it with APIs. The way it helps to achieve scalable throughput is by storing the contextual data in the grid and then moving the messages to the objects instead of moving the data in the objects to a computational pipeline external to a grid. By doing this, you eliminate many of the network transfers, and so you reduce the network overhead and improve the speed up. It also provides a domain for scaling, in particular scaling based on the twins themselves. So instead of creating Apache Storm bolts and trying to map them to servers, you just let the grid scale the number of servers as the number of digital twins increases. And this allows you to get very nice scalable throughput. It also allows for integrated data parallel analysis because the contextual information held in the digital twin instances can be operated on in parallel to be analyzed for aggregate patterns and trends, and this allows the user to maximize their overall situational awareness. So we've seen in-memory data grids as a software middleware layer on top of in-memory computing systems evolve from distributed caching to data parallel computing and more recently to stream processing. And so let's wrap up with a few takeaways from this tour through memory lane of in-memory computing. First of all, we realize it really has a long history. It dates back to 1983. I think most of us think of it going back to maybe 2005, but in fact, it has a long and storied history. The concept of scalable speed up was first tackled and has been driving design choices that since that time. And we don't speak about scalable speed up in most of our discussions, but it in fact is underlying the choices we make to ensure that we get performance scaling so that we have cost-effective use of an in-memory computing system. And we also see the shifting technology. In fact, the last talk talking about, and the earlier one by Terry talking about persistent memory. So, and as our technologies shift, we have to continue to balance our use of CPU memory and networking to always ensure scalable speed up. We expect, as Terry mentioned in the beginning, that live systems will continue to grow and generate more data to manage, and the data needs to be managed in a more comprehensive manner for customers. And so in-memory computing will serve as the key technology for extracting this value and for both live data and big data, and as we move forward into the future. So I hope this was helpful in giving you perspective on the in-memory computing architectures of the past and how it will help guide us in the future. Thank you very much.